So this video is, I've been calling it, or I'm thinking of calling it stepping stones. So before, the video before this I called it directions, and essentially these are just instructions for what you should do over the following few days after watching this video. So it's some instructions for reading and then thinking like what homework problems you should consider and also what's involved in the homework problems. And in this other type of video, so I'm just going to make these two types of videos. These are more like lecture videos. So some stepping stones, some things for you to really look out for, just to put them on your radar screen. So in the directions, I asked you to read about several applications of Schrodinger's equation. And I was just going to tell you what to look for as you are reading about them. So if you've already gone and read about them, you could look at these things that unfold on the page now in this video, and you could go fill in gaps or try to do some memory recall or see if you see what you can come up with on your own before going back to look at the book. But you should go back and review the book and see if you can address each of the issues that I bring up. So of course the first thing is somewhat of a review, but it's this one-dimensional infinitely deep well. That's kind of the first thing. And while you're reading about this, or actually after the fact, I wonder if you could answer questions like this. What do the solutions, and when I say solutions, I'm talking about the wave function psi of x, what do they look like? That is, could you draw a picture? How tall would you draw the picture? What would the axes be? You know, like if you drew a graph, do you know what function to draw, or do you just know what the function shape looks like? You know, is it a sine function, or is it something else that's stranger? Is it an exponential decay or growth? Yeah, and so after you say this, like, you might wonder, what about the energies associated with the different size or the different wave functions? You've seen that there is sometimes a quantum number associated with the wave function, and these energies, you might say that they depend on that quantum number. So the energy of the nth level, and this is the wave function of the nth level. It's a function of x. And then you can form probabilities from the wave functions. Probabilities. You might wonder, so what do these solutions look like? Did the book show you all of them, or tell you what they look like, or is there a limited number of the size? Like, how high does the number n go? Is n bounded? Does it start from 0, or does it start from 1? There is the issue of normalization, and what can you do with normalized wave functions? Well, you can do probability type thinking, but you can also do Heisenberg uncertainty principle thinking. Did the book show you any details about Heisenberg's uncertainty principle in this particular example? And what was that development as you would expect it? Like, what was interesting or strange about it, or, you know. Also, boundary conditions. As the book developed the solution to the one-dimensional infinite well, or developed the solutions psi of x or psi sub n of x, how did it sort of invoke the boundary conditions? How did it make decisions on what the boundary conditions have to be, and what did that do for saying what these wave functions, how do they look? So the boundary conditions, these are decisions you have to learn how to make. You have to impose boundary conditions. Yeah, so that's quite a lot of stuff to do just for this one-dimensional infinite well. When you go into the two-dimensional infinite well, so this will be the next stepping stone in your development of the subject at this point, quite honestly, it's the very same questions. What do the wave functions look like? Is there a way to write down the functional form? That is it sines and cosines? Or you might go and see that actually it's the product of sines and cosines for the infinite two-dimensional well. What do the energies look like? How about the quantum numbers? What was interesting in the two-dimensional well is actually there's two different quantum numbers. Something that comes up when you go up in dimension here is the first example of degeneracy. Like, what does this mean? Why is it important? So, yeah, degeneracy showed up. Up here, you could ask the same question. Why didn't degeneracy show up? Also, I'll point out that there was a technique that showed up here, separation of variables. Can you go and believe all of the steps that the book made in order to use the separation of variables to come up with how the wave functions, like what did they have to look like? And what were the energies associated with those wave functions? In the case of the simple harmonic oscillator in one dimension, really it's the same questions again. You might wonder, was there a degeneracy issue in here? What did the energy look like? What was the label? Did the label have an upper limit? Was there a maximum value on this quantum label? And then there is the last one was the finite well. And in particular, in this chapter, you just study the one-dimensional finite well. Yeah, same questions. Again, what do the wave functions look like? How many of them are there? What's interesting here is there's actually a very, very important qualitative change that occurs. There's a certain number of quantized energy levels in the finite well, and then an infinite number, and in fact a continuum number of energy levels non-confined in the well. This is a very interesting situation. We're going to continue to develop the finite well into the future, but for now, you could try to answer these same questions. What do the wave functions have to look like? The really cool thing to wonder about in this case is what is the boundary condition? How do you use them? And in the previous video, I described that there were non-analytic issues. What does this mean? I bet you'll find some really cool stuff if you look on the internet for the finite one-dimensional quantum well. The internet will show you some studies of this very issue. It probably is, maybe about 2 hours of thinking. So please do this if you have time or if you're interested, or both. But it's, you choose your own adventure for this part. I'd like to point out that, something very cool that shows up in your book. It shows up on page 157. And there's a paragraph. It's really just a paragraph long. It's about the simple harmonic oscillator. And how it's used to think about modeling for a diatomic atom. It describes something really cool about hydrogen chloride. It's a diatomic molecule. That's a funny thing. Diatomic atom. What the hell does that mean? Diatomic molecule. So HCl is it's described that in some ways, like the vibration modes, how the H and the Cl, so this might be the hydrogen atom and this is a chlorine atom, how they might be a little oscillator, and the energies of the oscillations follow. It describes the sort of experimental data that's associated with it, but the energies follow a harmonic oscillator energy level model. That is, the vibration modes of the diatomic molecule HCl, those vibration modes are quantized. It also describes that the harmonic oscillator can be used to model nuclear vibrations. So this is way down. So this is a diatomic molecule, but you can also go way down inside of one atom, a single atom, and look at its nucleus, and its nucleus is like a little oscillator that can be modeled, that has some similarities to the simple harmonic oscillator. So nuclear modeling. All right. Yeah, appreciate you listening to me again.